August 24th, 2001, midnight over the Atlantic. 306 passengers are fast asleep. They have no idea their aircraft is bleeding to death in the dark. No engines, no power. Just 19 minutes of suffocating silence. Most think a disaster is loud. For Flight 236, the terror was quiet. It wasn't a storm, it was a ghost. An invisible monster in the machine, killing the engines, one by one. Tonight, we enter the cockpit of a 200-ton coffin. We find the mechanics of misalignment and the microscopic error that turned a miracle into a death trap. It's a quiet August night over the Atlantic Ocean. Inside Air Transat Flight 236, nearly 300 passengers are sleeping or finishing their dinner as the Airbus A330 cruises smoothly at 39,000 feet. Without warning, the steady hum of the engine stops. The right engine dies first, followed 13 minutes later by the left. The main electrical generators shut down, plunging the cabin into total darkness and a heavy, unnatural silence. Suddenly, 200 tons of heavy metal became a powerless glider, dropping through the freezing night sky, hundreds of miles from any runway. Modern commercial aviation relies on strict physics and overlapping redundancies. State-of-the-art airliners carry meticulous fuel calculations with heavy reserves, making it nearly impossible to simply run out of gas mid-flight. The extreme rarity of this total fuel loss points to a slow-moving, invisible cascade of systemic errors that began on the ground. 9 days before the flight, maintenance crews discovered metal shadings inside the plane's right engine, indicating serious internal damage. Facing a tight weekend deadline to keep their flight schedule, they brought in a loaned replacement engine. The replacement engine was an older model, while the plane's internal plumbing was built for a newer design. When mechanics found the plane's hydraulic pump didn't fit the older engine, they forced a new generation fuel tube directly next to an older hydraulic line. These parts were never meant to work together. Once bracketed into place, the rigid tubes sat barely millimeters apart. The manufacturer's service bulletin expressly prohibited this mismatch. However, that critical document was sitting unread on an offline CD in the maintenance building. The technicians, struggling with a downed network, never saw the warning. This single moment of compromised procedure laid the physical groundwork for a disaster that no one in the cockpit could see. As the plane flew over the next several days, constant flight vibrations and pressure caused the hydraulic line to rotate. It pressed hard against the fuel tube, and the two metals began rubbing together. Hours of friction tore an L-shaped crack straight through the fuel line wall. High above the Atlantic, the plane began hemorrhaging fuel into the dark sky at a rate of 13 metric tons per hour. Despite recommendations made 4 years earlier to install automated fuel leak sensors in these jets, the manufacturer had not implemented them. The pilots were completely blind to the fact that their fuel was vanishing into the ocean. Eventually, the computers flashed a generic fuel imbalance advisory. The pilots, assuming a computer glitch, didn't immediately suspect a physical leak. Standard protocol required the crew to check the written fuel leak procedure. Instead, they operated from memory, skipped the leak check step, and decided to open the crossfeed valve. By opening the crossfeed, the pilots actively pumped the remaining healthy fuel from the left wing tank across the fuselage, dumping it directly out of the cracked pipe on the right side. The crew acted logically based on the incomplete data they trusted, but their actions directly accelerated the disaster they were trying to solve. With the engines dead, the pilots had one desperate target, a tiny military runway in the Azores Islands, over 140 kilometers away. A small propeller turbine, called a ram air turbine, drops from the belly of the aircraft to spin in the oncoming wind. This device provides zero thrust. It only generates the absolute bare minimum electrical and hydraulic power needed to keep essential cockpit screens lit and allow the pilots to physically move the wing flaps. The flight now rested entirely on the manual skills of Captain Robert Pichet.
Chapter 1 ends in silence.
But while the crew fights the dark over the Atlantic, the real disaster had already happened days earlier. To find the ghost in the machine, we don't look at the cockpit. We look at the hangar. This is the forensic truth of the failure. In dynamic, pressurized systems, a microalignment drift of mere millimeters causes the entire system to collapse. Consider a 300-ton, highly automated dynamic machine moving through the atmosphere. On August 24, 2001, Air Transat Flight 236 was traversing the dark expanse of the Atlantic Ocean, carrying 306 people from Toronto to Lisbon. A millimeter-scale mechanical misalignment, compounded by a human cognitive trap, transformed this modern engineering marvel into a powerless glider over the Atlantic. The Egyptians engineered the Khufu ship for the pharaoh's transit to the afterlife. It was designed to navigate a hazardous path using precise astronomical coordinates. Flight 236 was attempting its own high-stakes transit over the dark Atlantic waves, but the vessel's integrity was already compromised during its last maintenance window. On August 15th, technicians found metal particles in the right engine's oil system. Lacking a spare, Air Transat borrowed a replacement engine from Rolls-Royce, initiating a time-pressured installation window. The technicians lacked the required service bulletin because it was stored on an offline CD-ROM. This created a knowledge gap regarding the specific design differences of the replacement engine. Facing a strict Sunday deadline, the ground crew forced the installation of mismatched parts. They used a legacy hydraulic tube alongside a new design fuel tube. This CAD model displays the internal routing of the A330's Rolls-Royce engine. It identifies where the legacy hydraulic tube was installed adjacent to the new design fuel tube. This incompatible combination created a microscopic gap between the lines, violating the engine's engineered tolerances. Time pressure and inaccessible manuals led the technicians to override standard protocols. They ignored the requirement that these specific tubes must be replaced as a matched set. The aircraft flew several times in this state. The physical conflict between the tubes remained undetected during subsequent visual inspections by ground crews. The failure to verify the technical documentation bypassed the system's engineered alignment, planting a physical trap within the engine that would be triggered by operational stress. By the night of August 24, Flight 236 is cruising at 39,000 feet. At this altitude, the right engine is subject to continuous high-frequency vibrations. Under the stress of hydraulic pressurization, the legacy flange rotates out of its intended position, bridging the gap to rub against the fuel line. For hours, the two metal surfaces vibrate, slowly grinding down the wall of the fuel tube. The friction eventually compromises the tube's structural integrity. An L-shaped fracture ruptures, allowing pressurized fuel to escape. This chart plots the resulting fuel loss, escalating to 13 metric tons per hour, dumping thousands of gallons into the ocean. Despite the massive fuel loss, no alarm sounded. The Airbus A330 lacked a direct physical sensor for fuel leaks, relying instead on indirect data. The investigation reveals a chain of metal and paper, mismatched pipes, and unread manuals. But while investigators would later piece together the why, the 306 souls on Flight 236 were running out of when. 30,000 feet above the black Atlantic, the engines have gone cold. The sensors are dead. The miracle is all that remains. This is the landing. Forward to the night of August 24. Flight 236 is halfway across the Atlantic, and aviation fuel is hemorrhaging out of that fractured right engine at a catastrophic rate of 13 tons per hour. Shockingly, no alarm sounds in the cockpit. 4 years earlier, French authorities had recommended Airbus install an automated fuel leak warning system after a nearly identical incident, but the manufacturer never implemented the hardware. When the flight crew finally notices a stark drop in fuel on the right side, they fall into a well-documented psychological trap. They assume it is a mere computer glitch, a sensor error, not a physical leak pouring fuel into the night sky. Instead of pulling out the physical emergency checklist, the pilots rely on their memory. They decide to open the plane's crossfeed valve, a mechanism designed to balance weight. Opening that valve pumped the remaining fuel from the healthy left wing directly to the ruptured right engine, draining straight into the ocean. By relying on memory to fix what they thought was a software bug, the pilots mathematically guaranteed their own engines would starve. The plane is now completely dark, completely silent, and 144 kilometers away from the nearest piece of land, a small military airbase in the Azores. With the main engines dead, the aircraft deploys its last line of defense, the ram air turbine. This is a tiny emergency propeller that drops from the belly of the plane, spinning in the rushing wind to generate just enough electrical power to keep the essential flight instruments alive. But instruments alone can't land a plane. The man holding the control stick is Captain Robert Pichet. He is not a typical corporate airline captain. Years earlier, he served time in prison for smuggling drugs. That gritty background actually included years of working as a bush pilot, flying rough aircraft into remote lakes and dirt strips. He had the exact instinctual, seat-of-the-pants flying skills needed to maneuver a dead-stick aircraft. Without engine thrust, there's no chance for a go-around. Pichet has exactly one shot to perfectly align a 200-ton metal tube with a dark runway, or everyone on board dies. After 19 minutes of powerless gliding, the longest such flight in commercial aviation history, the massive jet drops out of the night sky and slams onto the runway at Lajas Air Base. With no engine reverse thrust to slow them down, the physical toll on the aircraft is brutal. The pilots apply extreme braking, which instantly locks the wheels. The tires blow out, and the massive landing gear violently grinds down to the bare metal axles against the tarmac. Sparks fly, small fires ignite, but the plane finally comes to a smoking halt. Against all engineering odds, all 306 passengers and crew evacuate safely. Not a single life is lost. Disasters rarely stem from a single massive failure. They happen when a series of unrelated vulnerabilities align perfectly. A missing offline manual, a mechanic shortcut, a missing warning sensor, and a cockpit memory lapse. Any one of these in isolation is harmless, but together they form a straight line to catastrophe. Flight 236 proves that while a chain reaction of human and systemic errors can easily cripple our most advanced technological marvels, raw human ingenuity remains our ultimate safety net.
Flight 236 changed aviation forever. It led to new sensors and stricter laws. But in a world of perfect machines, was it the tech that saved them, or the human spirit? What do you think? Was it skill, or was it a miracle? Let me know in the comments. Thanks for watching.